Hello and welcome back to Boxers Shorts, where we take ideas from GCSE Science and try and break them down and make them understandable. We are going to be starting a new unit with this video, which is from the chemistry area of the course, which is to do with the formation of the atmosphere. It is actually one of my favourite units to teach because it is both really interesting in terms of the way it looks at the history of Earth and how it's changed over time, but also because it leads into contemporary policy issues like global warming and climate change. Now, throughout this unit, there's going to be a lot of kind of backgrounds that I'm going to give you that you don't necessarily need to know. So what I'm going to do is I'm going to always try and identify the most important things for you to know. But a lot of the stuff that I'm going to be talking about isn't necessarily like the most important thing to know and take away and will come up in exams. But without it, you sort of won't really understand exactly what's going on. So let's get started. This here is Earth. That's the planet that we live on. And around the Earth is this kind of layer of gas, this really thin layer of gas that we call the atmosphere. Now, nowadays, the atmosphere is mostly, not massively, mostly oxygen and nitrogen. But it wasn't always mostly oxygen and nitrogen, and it's changed over time. Now, nowadays, the atmosphere is incredibly useful to us, and it has a number of really important, I guess, jobs that it does for us. Obviously, it doesn't know it's doing it for us. It just, it's just gas, but it does do a number of things that's really useful to us. One is it protects us from really nasty, harmful cosmic rays. So there's all sorts of horrible radiation coming from the sun that could damage us, but it gets blocked out by the atmosphere. It keeps us nice and warm and snuggy. So some of the radiation that comes from the sun is useful to us, and it's kind of heat, and it gets bounced around and trapped by the atmosphere. So it's a bit like a blanket around the Earth. Without it, the Earth would be really cold. And finally, it's this thing here. Why is it important to us that there's oxygen in the atmosphere? Say your answer on 3. Why is it important to us that there's oxygen in the atmosphere? 1, 2, 3. Probably a lot of you said something like, we breathe it. But that's not actually specific enough, because breathing is just the process of taking air in and out of your lungs. And so, you could take any air in and out of your lungs. Why is it oxygen specifically that's important for us? See if you can refigure or kind of rejig that answer and use a different bit of science. So why is it, what's the scientific reason that goes beyond just breathing in and out that we need this oxygen? Say your answer on 3. 1, 2, 3. I'm hoping you said something more along the lines of respiration. So respiration is the process by which we use the oxygen and glucose from our food. We use the oxygen from the air and glucose from our food in order to release energy, which our body needs. So like I said, the atmosphere is incredibly important to us, but it's not always been there. And it's important to talk about kind of the time scale that we're describing here. So humans have been around on the planet for about 200 million years, which is quite a long time. Sorry, did I say 200 million years? I did not mean 200 million years. I meant 200,000 years. Apologies. Even teachers make a mistake. I just made another mistake while I was doing it. So embarrassing. Okay, so humans have been around for about 200,000 years. The Earth, as it is, has been around for about 4.6 billion years, which is quite a lot more than 200,000 years. The atmosphere has been around for about that long. It starts getting produced as soon as the Earth is formed. The Big Bang, which is when it all started, why did it do that? I'll never know. The Big Bang, which is, sorry guys, which is where it all started, was about 13 and a half, I guess, billion years ago. So the time scales that we're talking about are enormous. We're talking billions and billions and billions of years. So how is the Earth formed? So originally there's this thing called the Big Bang. And I'm not going to teach you a huge amount about the Big Bang, except for the fact that everything that you see around you starts at the Big Bang. And initially, at the beginning, 13.5 billion years ago, they were just like lots of little specks of dust that had been produced, right? And some of them were just, a couple of atoms floating around in space, like this. Now, over time, and again, we're not talking like 5 minutes, we're talking billions of years. Over time, these particles start to become attracted to each other. What force do you think causes them to be attracted to each other? Call your answer to the screen on 3. What force do you think causes these particles to be attracted to each other? 1, 2, 3. I'm hoping you said gravitation, gravitational force of attraction, or just gravity. So these particles all kind of are pulled towards each other, and they bump into each other and they collide. And you might have one tiny particle and another tiny particle that bump into each other and make a bigger particle. Now, in turn, another tiny particle might bump into that one, or another big particle might bump into that one, and it becomes an even bigger one. And then eventually more big ones will bump together like this, and maybe some small ones as well. And they'll keep bumping and they'll keep bumping until you get a much kind of bigger lump, right? That's gets bigger and bigger and bigger and bigger as more and more pieces bump into it. Now, eventually these things, these massive like collections of particles, become the size of planets. And this is basically how Earth forms. So over time, something like this kind of big rock just builds up in space, and more bits and pieces join to it, more bits and pieces join and join and join and join. And eventually it becomes this kind of roughly spherical in shape object. And we might call that a planet. So Earth is a planet made of rock. Some of the planets are made of gas as well, so it's a bit more complicated, but Earth is a planet that's made of rocks. It's made of these particles of dust that all kind of join together. It is, however, a bit more complicated than that, because when you there's another thing that happens when they bump into each other. Not only when they bump into each other, so if we come back over here, so not only when they bump into each other do they stick together, but they also get very hot. Why do they get hot? Well, anytime you've got two objects in contact, so let's say you like rub your hands together like that, okay? So they start to feel a bit warm. Why is it that they start to feel warm? What is it that causes them to feel warm? And this is a physics word. Say your answer on 3. What is it that causes them to feel warm? 1, 2, 3. I'm hoping you said friction. So they start to feel a little bit warm. And yeah, so basically whenever two objects are in contact, there's a tiny bit of warmth, tiny bit of energy added to the thermal stall. So a tiny bit of energy is kind of is transferred there. If you move your hands faster, then obviously there's more energy. If you have bigger hands, then there's also more energy. So like my daughter, she's 3.5, her hands are small, she'll generate less energy than I will with my big hands. Now, if you imagine that your hands, instead of the size of hands, but the size of cities, right? So you take an entire city and rub it against another city. And instead of doing that like this speed, you do it at thousands of miles an hour and you just smash them together. You can imagine the amount of energy, the amount of heat that is generated there. So anytime these like two massive rocks in space smash into each other, there's a huge amount of heat and they form like a bigger rock like this, like a planet, but the planet would be really, really hot, super duper hot. And at first Earth will have been, mostly kind of liquid rock, just really, 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 really hot. Over time, of course, it starts to cool down and the surface here, this bit, cools down first. I guess it's a bit like, if you have like a jacket potato, right? A jacket potato is really hot. You take it out of the oven. Now, if you wait a couple of minutes, you can touch the outside. So if this was a jacket potato, you'd be able to touch the outside. But as soon as you open it, it's really, really hot on the inside. So that's a bit like what happened to the planet. And it cooled down a bit on the outside, but it stayed really hot on the inside. And this essentially caused this kind of thin layer of solid rock like this. So that would be solid rock. And on the inside, you've got, if we just did like a pie slice of the Earth, and on the inside, you had liquid rock. But this solid layer here wasn't completely continuous, and there were little holes in that solid layer. So let's kind of zoom in on that if we can. So there were tiny little holes here in this solid layer. We call those holes volcanoes. And volcanoes are like spewing stuff out the whole time. So to draw that now a bit bigger, what you would have is you've got your Earth like this, and you've got your liquid rock over there, and then you've got loads of tiny holes over here. And the volcanoes are just spitting stuff out like that. What are they spitting? They're spitting out some of this liquid rock, but they are also spitting out gases. Which gases? Mostly, let's do that again. Mostly CO2. What is CO2? Say your answer to the screen on 3. What is CO2? 1, 2, 3. I'm really hoping you said carbon dioxide. Mostly carbon dioxide and a small bit of water vapor, and potentially some other gases like maybe some methane, maybe some ammonia, but not really a huge amount of other stuff. So then, there definitely won't have been things like oxygen, but there will have been a small amount of water vapor, a small amount of ammonia, and a small amount of, I guess, things like methane, but not a lot. Now, those gases formed Earth's first atmosphere. They didn't just wander off into space. They stayed and clung to Earth. Why did they cling to Earth? Why were they, and I'll give you a big hint here, why were they attracted to Earth so that they did not kind of just wander off into space like this? Say your answer on 3. Why did they cling to Earth? What caused them to be attracted to Earth? 1, 2, 3. I'm hoping again you said gravity, and the gravity of Earth is what keeps the atmosphere where it is. And the most important thing for you guys to know at this point is that the volcanoes produce the Earth's early atmosphere, which was mostly carbon dioxide and had small amounts of other gases. So I've given you a lot of stuff there because I think that story is kind of important as we move from looking at what Earth is like today, what Earth was like 13.5 billion years ago, how the Earth formed, and how its atmosphere formed. So that's the formation of Earth's early atmosphere. Now, it is important to note before we move on that everything that I've said is what scientists call, one second, sorry, my screen's messing around, is what scientists call a theory. So scientists have ideas or theories, what we think is true. We can't necessarily know for sure. And we think that Earth's early atmosphere was mostly carbon dioxide, but we can't really be sure. And there's a good reason for that. And the reason for that is because it was so long ago. It's 4.6 billion years ago. We don't have any evidence from then. If I wanted to say, what was the atmosphere like last week? Right, well, I can go and ask a scientist and he'll say, right, well, actually, we took samples of the Earth's atmosphere last week and I can tell you exactly what it was. But we can't do that for what was like, 4.6 billion years ago because it's just way too long ago. So what that means is that we don't have a lot of evidence. So we make a theory. That doesn't mean we're inventing it, right? We've still got a decent reason for why we think it was like that. And we look at other planets, we look at other, kind of reactions that could be occurring at the time, and we simulate what the conditions would have been like at the time. So our theories aren't just guessing. We're not guessing. We're not making it up. We do still have, some evidence, but we don't have a lot of evidence, and that's why it's still a theory, and it's why people aren't 100% certain as to exactly what the atmosphere consisted, what the atmosphere was made up of. All right, so here are our kind of key messages and take-homes, and I suggest that you write this down as a note for yourself, because like I said to you at the beginning, the things that you really need to know, I'm going to signal to you. So write this down, please, pause your video, and then press play again when you're ready. Okay, so you should only be listening to my voice if you've written down those kind of key messages, key take-homes, key content, whatever you want to call it, don't really mind. And we're now ready to do some questions. So have a go for me, please, at these questions. And again, I remind you that if you are going to just sit there and just read them and think about them or not even bother doing them, then you're wasting your time with these videos. So do make sure you've got your paper, make sure you've got a pen, and make sure you do the questions. Press pause, and when you're ready, press play. Okay, you should only be listening to my voice now if you have done these questions. Thank you for doing those. If you haven't done them, again, I remind you that you are wasting your time. How long ago was Earth formed? So you should be marking your work now. About 4.6, sorry, that shouldn't have happened. About 4.6 billion years ago, or thereabouts. Obviously, we're being approximate here, but remember, 0.6 billion years is still 600 million years. So it's like, you know, if it were 4.7 billion years, that would still be 100 million years difference, which is, you know, well, put it like this: the dinosaurs went extinct less than 100 million years ago, so it's still a massive amount of time. What causes the small particles that eventually formed Earth to come together? So that'd be gravity, or gravitational attraction, or the universal attraction of matter, whatever. Okay. Why are scientists not certain about the formation of Earth and the composition of its early atmosphere? So here normally you get 2 marks, and one for saying it was very long ago, it was 4.6 billion years. Which ago, we're just saying it was very long ago, very long time. I don't think very long ago is actually a valid sentence. It was a very long time ago. And therefore, you say evidence is limited. What was the composition of Earth's early atmosphere? Mostly carbon dioxide and small amounts, not amounts, amounts of water vapor, methane, and ammonia. And depending on where you are in the chemistry course, you'll know more or less about compounds like methane, compounds like ammonia. The average surface temperature on Venus, so Venus is the second planet, Mercury is the first, Venus is the second, and it's hot. Boy, is it hot. It's 460 degrees. And like Earth, there is water vapor in its atmosphere. Suggest why there is no liquid water on Venus. So this is going to become super important in future lessons. Why do you think there's no liquid water on Venus, even though there's water vapor in the atmosphere? Well, the answer is because of how hot it is. Water boils. Sorry. My pen's really causing me some problems at the moment, and it's driving me a bit potty. Water is a gas. Water boils. Water is a gas above 100 degrees. So I don't think you could write just it's too hot. I think you'd have to be a bit more specific than that and say that water is a gas above 100 degrees, or Venus is so hot that water would be a gas. And then finally, how was Earth's early atmosphere formed? And we write there just simply from volcanoes releasing gases. Cool, that's the end of this video. In our next video, we are going to look at how the Earth's early atmosphere changed over time, and I look forward to seeing you again then.